Now I feel like I'm hearing echoes everywhere. Okay, so I think we're good. All right. So we started talking our last time, getting into electrons and electrons, how they move from one energy level to the next. And we're out sort of talking about electron configuration, as we talked a little bit about during discussion and all that. Is basically the order in which electrons go into the atom. And there is sort of special order, and it revolves around energy levels. And there's different energy levels, which are referred to as N, which is the principal quantum number. N equals 1 is the ground state, so that's the lowest in energy. And as you go up from that, N equals 2, N equals 3, N equals 4, and so forth, you get further away from the nucleus and higher in energy. So on the first energy level, there really is just one type of orbital, which is an s orbital. And these orbitals are really theoretical places where electrons are found within the atom. On the second energy level, there's a 2s orbital. There's also a 2p orbitals basically occur. On the third energy level, 3s, 3p, and that's when we first start to see actually our d orbitals appear. And on the fourth energy level, there's 4s, 4p's, 4d's. And it's up there where the f orbitals really start to appear. So understanding, as we'll talk about here, that basically first energy level s's start, p's start, d's start on the third, and f start on the fourth, will allow you to really write sort of any electron configuration you need, really come up with sort of the order correctly as to how those electrons basically go into the atom. They are, as I mentioned, housed in these sort of what are referred to as atomic orbitals. And there are s orbitals, p orbitals, d orbitals, and f orbitals. Any individual orbital could hold a maximum of 2 electrons. So any individual orbital, no matter which one it is, which energy level that it is, it can only hold a maximum of 2 electrons. In terms of how many there are of each of these different types of orbitals on each level, for an s orbital, there's only one type of s orbital. It's really a sphere, as you see there. It just gets larger as you kind of go from one energy level to the next. There's actually 3 different types of p orbitals that exist. They are sometimes referred to as px, py, and pz. And what that means is in 3-dimensional space, they're sort of oriented in different ways. Like in math, you have a little Cartesian plane, one on the x, one on the y axis, and one on sort of the z axis is occurring there. For d orbitals, there's actually 5 different types of d orbitals. And for f orbitals, there's actually 7 different types of f orbitals that occur. So that means that if you were to max out all of these sort of orbitals or subshell on each level, an s orbital could hold 2 total electrons always. The p, what is referred to as a subshell, could hold 6. The d subshell could hold 10 electrons, and the f subshell could hold a maximum of 14 electrons. The p orbitals, the d orbitals, and the f orbitals, all groups of those guys together on one energy level, are what are referred to as a subshell for each of those things, or a sublevel. So for example, if I went back to my picture here, if we were to take all 3 of these p orbitals, if each line represented a p orbital, that would be a 2p subshell. Or again, a sublevel. If I took all of these 5 individual d orbitals here, that would represent the d subshell, or the 3d subshell, or sublevel. And if I took all 7 of the f orbitals here together, all 7 of them would be represent the f subshell or sublevel. When we talk about s orbitals, because there's only one s orbital, it's just considered an orbital. It's not a subshell or sublevel because there's just one of them. Now, other terminology that we commonly use is level or shell. When we talk about a level or a shell, that is like everybody here on the n equals 2 sort of level. So that would be everybody that is there on the n equals 2 level, which would include the 2s orbital and the 3 2p orbitals all together. So when somebody says, you know, how many maximum electrons could you put on the n equals 2 level or shell, it would be a grand total of 8, because you could put 2 in the 2s and you could put 6 in the 2p subshell for a grand total of 8 electrons. There's actually a math way that you could figure that out if you want to know the maximum number of electrons on a level or shell. You take 2 times n squared. N is the principal quantum number. So the one that we just did was n equals 2. 2 squared is 4. 4 times 2 is 8. So that would be 8 electrons you could put on that entire level. If we did the third energy level, 3 squared would be 9. 9 times 2 is 18. And if you went across here, you could put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 electrons if you filled up that entire shell and our level. So if you want to quickly sort of calculate, if you max out a level without drawing them all there, you can use that little formula. You want to do the squaring part first and then times by 2 to get you what you need there. Any questions on that there? So if I said, how many electrons could I put on the n equals 4 shell or level, how many would that be? Yeah, it is 32. So 4 squared would be 16. 16 times 2 is 32. The n equals 4 would be everybody here with a 4 in it, right? All those little lines represent an orbital. If you fill them all up with 2 each, you would end up with 32 electrons. So it would be 32 electrons. How many electrons in a 3p subshell? In a 3p subshell or sublevel, we would be talking about just these 3 right here. Each could hold 2, which would be 6 in this case, right? And how many electrons in a 4f orbital? That would be the correct answer if it asks how many electrons in a 4f subshell. In a 4f orbital, it would be 2. Any one of these lines could only hold 2 electrons. That's the trick question that usually pops up on this, yeah. So any individual orbital can only hold 2 electrons, but if you had the 4f subshell, that would be all 7 of them together, then it would be 14 would be the answer. Any questions on those different sort of words there? Okay. And I made a nice scribble on all that. All right. What these orbitals are really what are referred to as being probability maps. They are, when we talk about electrons, the idea of electrons are they really do not move in pretty circles, like sometimes referred to as the Bohr model, and they don't move in these orbits in nice pretty circles. They move really randomly about the nucleus, and the best that you could do is basically think about the probability of finding an electron in a particular location within the atom. You basically have no idea how it's moving or where it's exactly at that point. And that's what's known as the Heisenberg uncertainty principle, which basically says the more you know about kind of where it's hanging out, the less you know about how it's moving, and vice versa, basically. So what these basically are atomic orbitals, which are probability maps of there's just a really high probability of finding an electron in this particular area. We would imagine that there would be a pretty high probability of finding an electron near the nucleus, since it's positively charged. Electrons are negatively charged. So there's definitely going to be an attractive force between those two, and we would expect to sort of find it near the nucleus. But again, it could be really anywhere sort of in these orbitals here. Here's just some pictures. That's a 1s orbital, a 2s orbital. Again, they're the same shape. They just get larger to accommodate more electrons. Sometimes people refer to these as figure eights. The p subshell there are teardrops, if you will. Now, there is an order at which electrons go in, and they do go into the atom, basically lowest energy first, and then they continue on to higher energy. And this is what all the sort of orbitals look like when there's just basically one electron present in hydrogen. And what we see here is like everybody on the second energy level is like all equal with each other. Everybody on the third energy level is like perfectly equal with each other. And that really doesn't hold true, because as you start putting more and more electrons into the atom, they are negatively charged, which means they really don't want to be near each other. So what happens is, as we populate more than one electron, these individual orbitals or subshells, they kind of shift in terms of their energy. So some become a little bit lower in energy and some become a little bit higher in energy. And that affects how electrons go into the atom, because they do pretty much go lowest energy, next lowest, and so forth as they're sort of filling. So what happens, as you can see here, when we start putting more than one sort of electron in an atom, we get a shifting in the energy of these different orbitals. So what happens is, it's actually the 1s cuts the electrons first, then the 2s, then it'll go to the 2p, then to the 3s, then to the 3p. And really the big change in energy occurs right around here. Actually, the 4s orbitals are lower in energy than the 3ds. So the 4s orbitals will get the electrons first, followed by the 3ds. And that pattern then sort of follows as well, the 5s before the 4d. So there's that difference in energy of these guys and how they come into the atom, the electrons. So definitely the 4s before the 3d. They're super close in energy to begin with, but the 4s is lower, so it should be filled first. So you could actually make the order at which electrons fill into the atom, and this is one version of it, this is another version of it. And either one of these things are things that you could really make yourself on a piece of paper. And if you're able to make this guy, and remember that pretty much you can max out 2 electrons in the s orbital, in the p subshell 6 electrons, in the d subshell 10 electrons, and in the f subshell 14 electrons. You can write pretty much any electron configuration that you would need. You always start up here at the very top, and basically what you do is you zigzag back and forth following the arrow. So here we would go down to here, then come back this way, then come back this way, come back this way. And you can see it takes you from the 3p to the 4s and back to the 3d, and you just kind of continue that pattern. So we just continue to zigzag until you basically fill in as much electrons as you need. So let's take a look here at electron configuration. We can write electron configuration by figuring out how many electrons an atom has. If the atom is neutral, it should have the exact same number of electrons as protons, which is the atomic number that you could get from the periodic table. So let's take a look here and we'll make our little thing. So to demonstrate how you can make that little chart we just did, if you remember what we just talked about, that on the very first energy level, the only thing there are s orbitals. And then on the second energy level, that's when p start. On the third, that's when d start. And on the fourth, that is where f start. Here's how you could create it pretty quickly. You just go 1s, that's where those guys start. 2p starts there, 3p, and 4f, not p, I'm sorry, d. If I remember my alphabet, that would be better too, I suppose. There, try that, there you go. We'll go with 3d would be good, maybe. 3d, there you go. Now, all you have to do after you kind of set it up like that and use the right letters, obviously, is really just fill in all the numbers below it. So the first one actually goes to 7. So you would go 2s below it, 3s, 4s, and then 5s, 6s, and 7s. Next, you would fill in underneath the P, so you would go 3p, 4p, 5p, 6p, and 7p. Then you would fill in underneath the D, 4d, 5d. This one actually only goes to 6. Truthfully, if you put 7, you'll never get there anyway, so you'll be okay if you went to 7. And 4f and 5f. And now you basically recreated that little chart just by remembering basically 1, 2, 3, and 4 is all you have to remember. Just kind of move them over and down. Once again, we will follow the arrows here. And so forth. And once again, we always start up here. All right, so let us write some electron configuration here. So we will start with, why not number 1 there? It's a good place. Number 1 is hydrogen. It has 1 proton, which means it would have 1 electron. So we would start at the very top, and that would take us right here to 1s1. And that is the way you write electron configuration. The first number is the principal quantum number. That is the energy level. That basically tells you it's on the first energy level. This tells you the orbital or subshell it is in. And the 1 at the very top, which is a superscript, tells you how many electrons there are in either that orbital or that subshell. Any questions on that one there? All right, continuing on here to helium, which is number 2. So once again, we will come back to the start here. And because we could put another electron here, we will obviously go back to here. So this will give us 1s2 in this particular case. Questions on that there? Can I put any more electrons into that s orbital? I cannot, because it is filled. That is 2 electrons. It's done, which means if we have more electrons, we have to go to the next lowest energy level, which shouldn't be a problem. So we'll continue on to lithium here, which is 3. Once again, we will start up here. So we're going to go with 1s2. At that point, we have filled it up. We're going to zigzag back to the next orbital, which would be that guy right there. And that would then be 2s1 in this case. Yeah. Yes. Yeah, so hydrogen's atomic number is 1, which means it has 1 proton. So if it's neutral, it should also have 1 electron, right? And so basically, if we're doing neutral atoms, which we are here, the atomic number, which is the number of protons, will also tell you how many electrons it has. So it should be equal to that number. So it'll be equal really to the number you see on the periodic table in this case. Other questions on that? This means I have how many electrons on the first energy level? 2, and on the second, 1, right? So I have 1 on the second energy level and 2 on the first energy level. I'm going to continue on here to the next one. So on the periodic table, number 4 is beryllium, which once again means it has 4 protons. So it should also have 4 electrons if it's neutral. Once again, starting at the very top here, we will go to 1s2. Zigzagging back now to our 2s. We're going to go 2s2. Can I put any more electrons into there? I cannot. So again, if I have more electrons, I need to go to the next lowest orbitals that are next. And that would be, if we zigzag back, we're going to zigzag back to the 2p, coming back up to the 2p. So why don't we do that guy with number 5 there, which would be boron. So boron has 5 protons, which means, again, it should have 5 electrons, starting once again at the very top here, 1s2, 2s2. And now I'm going to zigzag and come back to my p subshell here. And that will now be 2p1 in this case. You could count up all the top numbers, and that tells you how many electrons you got going on there. That is 2 and 2 is 4, plus 1 more is 5. So that is good. How many more electrons could I put in that 2p subshell before it's filled? 5 more, right? And then that would give me 6, and that one would be filled. So we could continue at this point to fill the 2p subshell because it's really made up of 3 individual orbitals, right? Which each could hold 2. So we could continue that process. And why not? We got some room on the screen. Let us see that. Number 6 there, we'll go here is carbon. Carbon has 6 protons, which means, again, it should have 6 electrons starting at the very top. Once again, always, we will go 1s2. We're going to then go to our 2s2. And now our 2p2 at this point. How many electrons are in the first energy level? 2, yes, 2. How many are on the second energy level? It is 4, 2 there and 2 there. They are both on the second energy level, yeah? So those are 4 electrons on the second energy level. We have 2 of them hanging out in the S sort of room, if you will. We got 2 hanging out in the P room over there, but they're both on the second energy level. Any questions on that there? All right, so while we finish out the first 10 there, we'll continue down. We will go to nitrogen, which is 7. So once again, here we will start at the top, which will be 1s2. Zigzagging back to our 2s2. Coming back to our 2p, which we will now put a 3 on it. How many more will go into my 2p subshell before it's filled? 3 more before it's filled. We're halfway filled. By the way, they go in just so if you want to kind of visualize it, if this is our 2p subshell, they actually go in, if the arrows are electrons, 1 at a time. Actually, they go 1 into each of the individual orbitals first. That would be like your px orbital, your py orbital, and your pz orbital. At this point, once they kind of fill up all the individual orbitals, kind of go in one direction, then they actually come back and start pairing off. So they actually do go in 1 at a time, and then they pair off the electrons. This is a rule known as Hund's rule, which means they have maximum parallel spin. So as you can see there, we do have 3 spots, 3 more spots, 1 in each of the orbitals still left. So we'll finish with oxygen here, which is number 8. So starting at the top here, we're going to go 1s2. Next one will be 2s2, and now 2p4 at this point. Once again, if we count up the top numbers, we got 2 is 4, and 4 more is 8. We have 2 electrons on the first energy level, and we got 6 electrons here on the second energy level. And again, to show you where it would go, it actually would go here. That 4th electron would fill into that little orbital right there. And then fluorine is number 9. So that would be 1s2, 2s2, 2p5 at that point. Again, the next electron would actually go here. And as you can see, there's really space for just 1 more electron in that p subshell. And that would happen at our good friend there, neon, right? Which is 1s2, 2s2, 2p6 in this case. At this point, as you can see from my picture, there's no more room for 2p subshell. Would then has to move on to the 3s, would be the next lowest energy orbitals that would get electrons. Question on that there. All right, so why don't you do the electron configuration 4? Why don't you do calcium, which is number 20? And why don't you do nickel, which is 28? Okay, let's take a look and see here. So we'll start with calcium, which is 20. Once again, the 20 really is the atomic number, which is the number of protons from the periodic table. And once again, since we're assuming that this is neutral, it will also then have 20 electrons. So we're just going to start at the very top here like normal. So we know we could put, if I get that circle to make it there, we could put 2 of them there. So that's going to be 1s2. We then would zigzag to our 2s2, which would fill that up. We then would come back and zigzag here, and that could hold 6. If you're not sure how many you put in there, once again, you can just count the top numbers. That's 2, 2, and 4 is 6 and 10 at the top. So we need to continue. So we'll go with next our 3s2. Zigzagging back here, we're going to go to our 3p6 at this point. That is 18 electrons. We're not done. And again, this is where it is different than a lot of people think. It actually then goes to the 4s because they are lower in energy. And we would go with 4s2. And that would be our calcium in this case. Any questions on that configuration there? Going to nickel, looks like. So nickel is 28. Once again, that's going to be its atomic number and number of protons. So we'll start up on top. That's going to be 1s2. Then rolling next will be 2s2. Rolling back there to our 2p, which would come next, and put 6. We're going to go into our 3s2. We're going to roll into our 3p6. We're going to go next to our 4s2. That's calcium, basically, what we just wrote there. That's 20. Next, as you can see, as we come off of 4s, we are going to come back now to the 3d. So the 3d is the next one that can take it. You could put 10 electrons in there, but in this case, we do not need 10 electrons. I think we just need about 8, if that's not right. We just need about 8 electrons there, and that would be nickel's configuration. First off, any questions on those configurations? Yeah. Yeah, so in any of the subshells or orbitals, you don't have to completely fill them. So you just need to fill them to what you need to get you to your number. Yeah. So they do not have to end up being completely filled or anything like that. In some cases they will, and then a lot of cases they won't. But you just basically put in what you need. Other questions? Okay, so these are electron configurations for calcium and nickel. And if we look at, for example, here, calcium, up through this part of it here, that is how many electrons? That is 18 electrons. And who on the periodic table is 18? That is argon. So there is a shorthand that you could do when you write electron configuration. You could put a bracket and argon and configure and brackets. That means the electron configuration for argon, and then you would just continue on, and it would be 4s2. So that is what you would do for something like calcium if you wanted to kind of do the shorthand. We could also do that for nickel up to nickel. There's same thing up to here is still 18, which was once again be our argon's configuration. And we could write argon and continuing on 4s to 3d8 for nickel. Argon is group 8 on the periodic table. It is what is known as a noble gas, which means, frankly, what goes in the brackets here has to be from group 8 noble gases. So it is the noble gas that comes right before the element. So, you know, if you were doing, say, something like sodium, you would go beat one back from sodium on the periodic table, and you would find their neon. And then you would continue on to sodium with 3s1. So this is what is sometimes referred to as noble gas configuration. When you do a kind of shorthand, it has to be somebody from group 8 on the periodic table. And once again, group 8 is the very last group there. Helium, neon, argon, krypton, xenon, and so forth. So it's got to be somebody from this group into the brackets there from the periodic table, and then you continue on with the configuration. Any questions on that there? Now, there are a few exceptions to how electron configuration would go, or you would predict it would go. And there's a number of exceptions, but the two that most people in most classes are concerned with is chromium, which is 24, and copper, which is 29. Now, if you just followed our zigzag sort of back and forth pattern there, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 as the electron configuration here for chromium. And if you did the same thing for copper, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9, or if you want to shorthand it, argon 4s2, 3d4, or argon 4s2, 3d10, 9. Now, where the exception actually occurs is it's been found experimentally that because these orbitals are really close to each other, it's actually been found to be more stable with an extra electron up in the d orbital from the s orbital. So the correct sort of electron configuration for chromium and copper is actually not these. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So that is the sort of exception there. 4s1, 3d5. It has one extra electron up in the d orbital, one less electron in the s orbital. It's more stable that way because it maximizes one electron in a parallel spin with everybody. Copper has pretty much the same deal. It would be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1, 3d10. So 3d10 there for copper, our argon 4s1, 3d10, our argon 4s1, 3d5. So these are two exceptions to the normal electron configuration you should be aware of. And again, the exception, basically one more electron in the d, one less electron in the s. They are able to really do that very easily because frankly, those orbitals are like super close in energy anyways. They actually switch in energy once you start filling the d orbitals. So although the s orbitals are less in energy when the electrons go in, as you get to filling the d orbitals, they actually switch back the other way. And the d orbitals are lower in energy than the s orbitals. And that's why you sometimes see electron configuration written like all in order, like all the threes together, all the fours together. And that's based on energy rather than filling. When you write electron configuration, you should do it like I just showed you, because that's pretty much how everybody does it in chemistry, which is the filling electron configuration, not the energy sort of way. Any questions on that? Yeah. There's just been found experimentally to be that way, be more stable that way. Yeah, and it's really because of this, the 4s orbital and the 3d orbital, they are like super close in energy to begin with. So it doesn't take a lot to sort of convince, this electron that was normally down here to kind of go up here and fill it in. And like I even said before, what actually happens once you start filling in the d orbitals is they actually switch in energy, and it actually becomes a 4s that ends up being higher in energy once electrons actually go into the d orbital. So it's kind of a weird thing. It affects when these guys lose electrons as to which electrons they lose, because there's that switch that occurs. But to answer your question, it really is just experimentally it's been found that those two have a more stable arrangement with this type of electron configuration. And to be truthfully honest with you, if you look at where chromium is and sort of copper on the periodic table, and if you go down from them and kind of in, there's like a ton of exceptions that actually are in that area of the periodic table. For example, something like PD, it has no electrons in its s orbital. They've all been moved up to the d orbitals and stuff like that. Silver is actually an exception as well. So there's a lot more exceptions. You can find most of them kind of on the periodic table right below those two elements, and then kind of down and in. But for us and most chemistry classes that you take, it is just chromium, copper, the two that you should know. So for us, we will do the same thing. You are responsible to know chromium, copper has this special sort of configuration. Everybody else, you could just follow the zigzag thing and write it, like we talked about, and it'll be fine. Just know in real life, if you kind of have an element below those guys and in on the periodic table, there's probably some more exceptions that you would normally run across. But for us, chromium and copper are the only ones you have to worry about. Any questions on that? Yeah. Argon?
Yeah. What would be the last numbers, like 4s1, 3, 5?
I'm not sure I understand what you're saying.
Those last two numbers.
That's the rest of the electron configuration to get to 24, because basically argon only represents 18 electrons. Then that would be 19, and then that would get us to 24 electrons. So when you do that noble gas configuration, you basically put those noble gases in brackets, and that represents however many electrons they have, and then you need to kind of continue on with the configuration until you get to whatever you need to stop at. Yeah. But it's always whatever element you're writing in electron configuration, it should always be the noble gas there in group 8 that came right before it. So you got to kind of go backwards to that last one and then pick up from there in terms of the configuration. You want to go forward, so you go backwards and then pick up. Other questions on that? Yeah. So let's talk a little bit about what happens when maybe things get charges. So let's say we did have nitrogen. Let's say it had a -3 charge. That is what is known as an anion, right? It has a negative charge. Negative, I think we talked about maybe when we were doing protons, electrons, and neutrons. Negative means that somebody has gained electrons. And how many gained is basically the number that's there. So normal nitrogen with no charge has an electron configuration of 1s2, 2s2, 2p3 here. And has 7 electrons there. -3 means that it gained actually 10 electrons in this case, which means its configuration would be 1s2, 2s2, 2p6. If we look at something like magnesium, which is 12 electrons, it would be 1s2, 2s2, 2p6, 3s2. If we have magnesium that had a +2 charge, the plus means that this is a cation. It has lost electrons and it's lost 2 electrons, which means this guy would now have 10 electrons, which means its configuration would also be 1s2, 2s2, 2p6. 10 electrons is who on the periodic table? It is neon, right? So you could just write neon there, right? It's basically neon's configuration. All 3 of those things, nitrogen with a -3 charge, magnesium with a +2 charge, and neon with no charge, they all have the same electron configuration. And that is what is known as being isoelectronic with each other. So if somebody says these guys are isoelectronic, that means that they have the same electron configuration as each other. If we look at the periodic table, what happens here is really kind of the basis of bonding, and what everybody's trying to do is everybody's trying to get to the noble gas configuration to have the same electron configuration as noble gases. Noble gases are incredibly stable, and that's what everybody tries to achieve. If we look at where, for example, nitrogen is on the periodic table, there's oxygen, fluorine, and then neon. He started here at nitrogen. He gained 3 electrons, which basically moved him 1 place, 2 places, and now he is sitting at the same electron configuration as neon. So nitrogen, in this case, by gaining electrons, allows itself to get to the same electron configuration as neon and become very stable in that sort of situation. And that's sort of the goal of it. If we look at where magnesium is, for example, on the periodic table, magnesium is like right about here, and then there is sodium. Then if we back up way over here, there is our neon. Now magnesium started right here. It actually lost 2 electrons. So when it lost 2 electrons, it went 1 electron and then back 2 electrons, and it backed up to neon's configuration, which once again is a noble gas configuration and very, very stable. So in the case of magnesium, when it loses those electrons, it's able to reach the same electron configuration as neon. Just so we're clear, it does not become neon, and neither one of them become neon, but they have the same number of electrons as neon. So they're very much like neon in the sense of how many electrons they have, which makes them really, really stable. That is really the basis of all bonding. Ionic bonding and covalent bonding is. In ionic bonding, metals typically will lose electrons and go back on the periodic table to the noble gas that comes right before them. Nonmetals will typically gain electrons and move forward on the periodic table to the same noble gas that comes right before them or right after them. And that's how they sort of achieve that really stable situation. Any questions on that there? Now, transition metals, which are sort of like what we were dealing there with nickel, for example, and iron and things like that. Iron is a transition metal, and they actually behave a little bit different than other things. So iron, which is 26, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now, when iron gets its electrons, as we just talked about, they do go into the 4s orbitals first, and then they start to fill up our d orbitals, again, one at a time, and then actually come back and pair off. What happens, as I was talking about, is at this point, once we start basically filling those d orbitals with electrons, they actually switch in energy. And what ends up happening is the 4s electrons actually become higher in energy than the 3d electrons that we had. Now, this affects, for example, something like iron and most transition metals when they go to lose electrons. So they typically will lose electrons, become positively charged. So what happens is when something like iron now gains a +2 charge, instead of having 26 electrons, +2 would mean it has how many electrons? 24 electrons. It's actually going to lose 2 electrons. Now, because this switch in energy occurs, things always lose the highest energy electrons first. So when something like iron goes to lose those 2 electrons, it is actually going to lose those 2 right there first. So it's always going to lose the s electrons first. And this happens only for transition metals, like between group 1 and group 2 and group 3 there on the periodic table, which means the electron configuration for iron would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 are argon 3d6. It is these 2 electrons that actually get lost first. So it's a weird thing that happens, and only happens with those type of elements. The electrons go into the s first as they are filling, and then the d. But then there's a switch that occurs in the energy once you start putting the electrons into the d. So where it really affects is when these guys lose electrons, which ones they lose first. Now, let's just say iron had a +3 charge. That means it actually would have 23 electrons, right? So it means it actually lost not 2 electrons here, but it did lose 3 total electrons. So it happens the same way. It's going to actually take, once again here, the 2 electrons from there, but I need 1 more electron, right? So now that I get rid of the 4s, what would be the next lowest? It would be the d. So now we would actually dip into the d here and take one electron out of it. And what would happen at this point is we would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 in this case, or argon 3d5. So transition metals, which basically on the periodic table are right about here, Sc to like zinc and down on the periodic table. These guys, when they do go to lose electrons, will always lose the s electrons first, and then if they need to, they'll go into the d. What happens with those guys in transition metal region is this: they don't get back to the noble gas. So they don't get themselves back to the noble gas configuration, because in a lot of cases they would need to lose like 12 electrons to back themselves up there, and that's a lot of electrons. So they typically don't get themselves back to noble gas configuration. But everybody sort of outside of that area, for the most part, will get themselves back to a noble gas configuration when they gain and lose electrons. Any questions on that there? So why don't you try one here? Why don't you do oxygen with a -2 charge, and why don't you do nickel with a +4 charge? What is the correct electron configuration for both of those? Oxygen with no charge is 8 on the periodic table. Nickel is what we did earlier, which was 28 on the periodic table. So take a second or two, write the correct. Okay, let's take a look here. We'll go oxygen and nickel here. So we got oxygen, which with no charge is 8, which we wrote the electron configuration previously, 1s2, 2s2, 2p4 in this case. Oxygen with a -2 means the minus, it has gained electrons. The 2 is how many it gained from the neutral guy, which means we are going to end up with 10 electrons. And they fit really nicely right about there, because the p subshell can now take in 2 more, right, until it's filled. And that is where they will end up as 1s2, 2s2, 2p6. Or again, that is neon's configuration. Yeah. Any questions on that one there? Nickel, which we did before, was 28. That was a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 8, I believe. I was going to go with 10, but that felt wrong. Let's go with 8. At this point, when the nickel makes a +4 charge, the plus means it has lost electrons, and 4 is how many it lost. So it goes from 28 to 24 electrons. This is one of those transition metals where there is that switch that occurs in terms of energy. So the first 2 electrons are going to come out of here, and we still need 2 more electrons. So then we're going to have to dig into the D, which would be the next highest at that point. Doing all that good stuff will leave us 1s2, 2s2, 2p6, 3s2, 3p6, and then we should be down to a 3d6 there at the end. Or that is argon 3d6 happening. Any questions on either of those electron configurations? Yes. I'm sorry, say again. It is Ni. That's actually, that is a bad I. It's not 2 dots. Let me make it better. There you go. Yeah. So it is Ni. Yeah. Other questions? Okay. Questions on electron configuration, things with charges, things with no charges. You only take away from the one before when it's a transition metal. Everybody that knows representative elements, which is like your group 1, 2, 3, 4, 5, 6, 7, 8. Those guys, for the most part, will either be you're taking away from the one at the end, or you're putting them into the one at the end. But it's just the transition metals, because it has that switch in energy that occurs, that you always take the S first, and then if you need more, you always go into the D. So for transition metals, it's always S first, and then if you need D. Everybody else, if you're taking away, should be a guy at the end, and if you're putting it in, or they're gaining, should go into the guy at the end as well, the representative elements. Other questions on that? All right. So by the way, in case I didn't say this, is the way you should write electron configuration. I don't know if they still do it crappily in your lab manual with like just numbers like 2, 8, 10, 12, who do we appreciate type thing. Don't write it like that. Write it like this. Any questions? Okay. Let's see here. We can also, if you wanted to, and you know what you're doing, those are two very important things there. You can take a periodic table like so, which is a 1, 2, maybe 3, 4, 5, 6, 7. And you can actually count off electron configuration from the periodic table. The first two groups are what are referred to as the S block, and that's because S can hold 2 electrons, so 1 spot, 2 spots. Groups 3 through 8 is what is referred to as the P block, and that is 6 spots on the periodic table if you count it. 1, 2, 3, 4, 5, and 6. And that is the P block. The transition metal is the D block. D is 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the F block, which are the 2 rows on the bottom, that is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. You could use the period numbers as like the 1s, 2s part of it, and you could actually count it off just to demonstrate how it would work. Right about here, this spot right there would be sodium. So if I were to do this, I would count it off like this. We would start at the very top, which is where hydrogen is. That is 1s2 to helium. Then we would go 2s2 to beryllium. Now we would come over here to our P, which is still on the second row, and that would be 2p6 all the way to the end to neon. Then we would come down here to our third period, and that would be 3s1. So you could actually just count off the electron configuration. You do have to kind of know what you're doing, because if you get to say iron, which we did as well, which would be approximately right about there. If we were to do iron, for example, we would start at the top here. That would be 1s2 to helium, 2s2 to beryllium. From boron to neon would be 2p6. This would be 3s2 to magnesium, 3p6 from aluminum over to argon. What comes next is 4s2 right here, which is SC on the periodic table. That is the d orbitals. That's where they start. And what energy level did the d orbitals start at? What energy level do they start at? Yeah, kind of that thing we wrote, right? 1, 2, and 3, right? S, P, and D, right? And then F. So they start at the 3. So although it is sitting here on number 4, that is not 4D, that's actually 3D. And that would be 3D 1, 2, 3, 4, 5, and 6. So you have to keep in mind, if you want to count it off the periodic table, that's actually 3D. The D are 1 behind the period number. And technically this is the F's, which means that's 4F, which actually goes right about there, which is actually 2 behind the period number. I would highly recommend not doing it. I would highly recommend just doing the zigzag thing, and you should get the right answer all the time. But if you want to check yourself, you could look at the periodic table. But there's a lot of places, especially in transition metal region, if you're not really paying attention, you might get the wrong sort of configuration. Any questions on that there? Okay. All right, so we talked about this. So I'm just going to kind of scroll through it, writing our noble gas core. All right. So to finish up this chapter about some things, first off, it's the valence electrons. Valence electrons are the outermost or highest energy level electrons there are. They are really important because they are the ones involved in bonding. Because they are furthest away from the nucleus, they're not held as tightly, which means that is why they're involved in bonding. They're easily either given away or they're easily sort of shared with electrons. So if we write the electron configuration for nitrogen, which is 7, 1s2, 2s2, 2p3, once again, we have 2 electrons on the first energy level. We have 5 electrons on the second energy level. So these would be the valence electrons here for nitrogen, which would be 5. The lower level electrons are what are referred to as core electrons. Core electrons are the ones closer to the nucleus. They are held a lot tighter. They are not involved in bonding. Just the valence electrons are involved in bonding. You can do that for everybody. We just wrote sodium's electron configuration, I believe. 1s2, 2s2, 2p6, 3s1. Highest energy level here is 3. Yes. And it has 1. So that would be the valence electron for sodium. These would then be the core electrons for sodium. You could also do it for oxygen, what we did as well. Oxygen was 8, 1s2, 2s2, 2p4. Oxygen has how many valence electrons here? It would be 6, as these are both, all 6 of those are on the second energy level. So that would be the valence electrons, 1 and 6. And that would be the core electrons. So you absolutely could write the electron configuration for everybody and figure out which one is the highest energy level, but who has time for that? So it's much easier to go to, we had a periodic table there, to go to a periodic table, and basically the group number equals the number of valence electrons. So group 1, 2, we're talking 3, 4, 5, 6, 7, and 8. So everybody in group 1 has 1, everybody in group 2 has 2, 3, 4, 5, 6, 7, and 8. The only exception for 8 is helium. It has only 2 electrons total, so it can't have 8 valence electrons. So it has only 2 electrons. That's why sodium, which is group 1, had 1 valence electron. That's why nitrogen there was group 5, so it has 5 valence electrons. And our oxygen there was group 6, has 6 valence electrons. So that's a much easier way to do it. For your transition metals, most people will say they got the s electrons there, are our 2 electrons. So for transition metals, as we talked about, they will always sort of lose. Whoops, go back here. Where'd you go? There it is. We'll do that. For our valence electrons, remember that they will pretty much always lose these s electrons first. So most people consider the 2 electrons there the valence electrons. But as we saw, you can dip into those Ds if needed for the transition metals. The good news is we don't deal too much with transition metals and bonding and stuff like that, so it doesn't worry too much about it. But a lot of people will say 2 for those guys. Some may say a little bit more because you can't go into the D electrons for the transition metals. So as I mentioned before, the number of valence electrons will equal the group number. So fluorine, which is group 7, has 7 valence electrons. Chlorine, group 7 as well, also has 7. And carbon, for example, is group 4, which would have 4 valence electrons. So let's talk a little bit about metals and nonmetals. As you go down a group, especially with metals, they tend to give away electrons a lot easier. So in order of losing electrons, cesium is more than rubidium to lithium. This is because the outer electrons are further away from the nucleus, that positive charge, so they're not held as tightly. And the most active nonmetals are found in the upper part of the periodic table. So when we look at a periodic table, there are a couple of trends which are really important. One is ionization energy. And ionization energy is the energy required to lose an electron or remove an electron from an atom in the gas phase. Electrons actually come off one at a time. They actually don't all just pop off at once. They do actually occur one at a time. So for example, if you took something like magnesium, if I could get there, there we go. First thing would happen is magnesium would pretty much dump 1 electron and become positively 1 charge. This is what is referred to as the first ionization energy. That would be the energy required to remove the first electron, say, in magnesium. The next thing that would happen is magnesium would then lose a second electron. And that would be what is referred to as the second ionization energy. And let's just say, for example, maybe magnesium wanted to try to lose a third electron. That would be what is known as the third ionization energy. Is it easier to remove the first electron from magnesium or the second one? Which one's easier? What do you think? It is easier to remove the first electron, right? First electron is neutral. You remove the first electron. Does the thing get larger or smaller when it loses an electron? It gets smaller, right? It loses some electron cloud, so it gets smaller. Also, it gets more positive, right? And now you got a greater positive charge, and you're trying to remove something that's negative. So when you try to pull off that second electron, it's going to take a lot more energy to try to do that. So you take off the second electron, size gets smaller again, right? Larger positive charge now. You want to try to remove the third electron, gets much, much harder every time you try to rip off an electron. So between the first electron to the second electron to the third electron, it gets much, much harder, and the ionization energy increases a lot as you go from first to second to third. In general, if you look at the periodic table, as you go from left to right, the ionization energy increases and it decreases as you go left and down. And individually, as you continue to pull off electrons, it gets much, much harder. Magnesium usually will make a +2 charge. That is why. Why is that, do you think? How many valence electrons does magnesium have? 2. So once you remove those 2, which mind you is kind of hard, gets harder. Now, if you want to remove the third electron, those are no longer valence electrons. These are now core electrons, which are now even closer to the nucleus. Doesn't happen. It becomes like almost you need 10 times the amount of energy to try to remove that third electron than the second. And just energy-wise, it doesn't really happen. So that's why some things only can form a certain charge, and magnesium is one of those. It will always form a +2 charge, because past +2, there's no chance in the normal conditions you're going to be able to rip off that extra electron out of there. So, and that's because you're getting into those core electrons, which are really, really close to the nucleus. Atomic size of atoms, it decreases as you go to the right of the periodic table and up, and increases as you go left and down. And a couple other important trends here we'll add to our periodic table is electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. On the periodic table, it increases as you go up and to the right, and it decreases as you go down. Also, electron affinity is sometimes referred to. An electron affinity is the energy change that occurs when you add electrons. It also has the same trend as above there. It increases as you go to the right and decreases as you go to the left. So all these sort of periodic trends work together with what we know. As you go up and to the right, you're in the non-metal region. And as you go up and to the right, you have things that have very high ionization energy, which means it takes a lot of energy to remove electrons. You have things that have very high electronegativity, which means they want to actually bring electrons towards themselves. And you have things with high electron affinity, which means they like to gain electrons. In addition, they're very, very small to begin with. So even their outer electrons are a lot closer. So all those things tell us when you go up and to the right on the periodic table, where nonmetals are, they typically like to gain electrons, which is typically what happens. And that's why the most reactive nonmetal can be found in the upper right, because of those trends of very small. As you come up and to the right, you are very small in size. You have high electronegativity. You have high ionization energy, and you have high electron affinity. All of those things are our nonmetals that like to gain electrons. As you come down this way on the periodic table, you have all the opposite. You have very low ionization energy. You have a larger size. You have smaller electron affinity. And you have smaller electronegativity. All those things are basically, I have a very large size. My outer electrons are far away from the nucleus. They're not held as tightly. If you like to remove them, you can do it very easily with a little bit of energy. I'm not really interested in gaining any electrons or bringing electrons towards myself. Take my electrons, please, is pretty much what happens with our metals. So that's why metals typically will lose electrons because of those trends. They have all the trends that pretty much say, just go ahead and take my electrons. Non-metals, on the other hand, are typically ones that will gain electrons because they have the opposite trend of bring the electrons towards me. I want to keep my electrons and take your electrons. And once again, that is why upper right of the periodic table is the, again, most reactive non-metal. That guy right there, by the way. And lower left there, the periodic table, where really francium is, that's not pictured here, is sort of the most reactive metal that you can find. Remember, metals are this way, right? Non-metals, upper right of the periodic table, right, is where we find those guys. Any questions on any of those trends? Okay, let's see here. Okay, so I think that pretty much wraps up this chapter here. We will lay it up there. Let's talk about